Hello students. So, in the last lecture I have discussed creation of carbon 12, and we have seen how beautifully carbon 12 is created because of a two-step process called as triple alpha process. So, quickly let me summarize the previous lecture. In the triple alpha process, which is a two-step process, initially beryllium 8 is formed, and by reaction between beryllium 8 and alpha we have carbon 12, and it is the resonance state within the carbon 12, because of which the rate of reaction is inconsistent with the ratio. All right. And in today's lecture I will share some of the salient features of survival of carbon 12. So, last lecture we have discussed creation of carbon 12, and in today's lecture survival of carbon 12. All right. So, what are the nuclear reactions which play important role in the survival of carbon 12, and then blocking of quiescent helium burning. All right. So, in the helium burning we have seen in the core of the star, it is a red giant basically, and why we call it as a red giant already I have discussed in the basics of helium burning. Okay. And there is a stage when this helium burning phase, the quiescent helium burning stage blockings. What is the reason for it? And then what are the other important helium burning processes or reactions that we will discuss in today's lecture. All right. And finally, I will summarize the helium burning by putting some perspectives on helium burning reactions. All right. Then in the survival of carbon 12, remember how the stability gaps at masses A is equal to 5 and A is equal to 8. Okay. How stability gaps at masses A is equal to 5 and A is equal to 8 were bridged by the triple alpha reactions, isn't it? And it was clear that carbon 12 is formed within the star. Now, the issue is that because carbon 12 is fourth most abundant element in the universe, how it survives we have to understand. So, that is one of the important topics of today's lecture. So, carbon 12 is the fourth most abundant element, and this is a very important number in the nuclear astrophysics, that is the ratio of carbon to oxygen. It is not greater than 1, it is less than 1. That is the reason why oxygen is the third most abundant after helium and after hydrogen and helium, and then comes carbon. So, carbon to oxygen ratio is 0.6. This we have to keep it in mind. I am not going to discuss how people have measured it, okay, but I am discussing how nuclear reactions have to proceed, with what rate it has to proceed, so that this ratio should be maintained. All right. Now, this helium burning of carbon, if you see, the alpha reacting with carbon 12 gives rise to oxygen 16, and the ratio of carbon to oxygen is 0.6, isn't it? Whether it has to proceed through a low rate, moderate rate or high rate, how to know that? How to know whether the rate with which the alpha plus carbon 12, that means we are discussing the survival of carbon 12, and we know the carbon to oxygen ratio is 0.6. So, the reaction of alpha plus carbon 12 has to proceed by moderate, high rate or low rate. See, it is very clear that in the universe, when we assume that carbon is formed within the stars, it is a direct product of alpha plus alpha, right, direct product of triple alpha reaction. In the universe, majority of the abundance of carbon is the direct product of triple alpha reaction, So, it is sensible, it is logical to assume that if carbon 12 is the direct product of the triple alpha process, then the rate with which this alpha plus carbon 12 has to proceed should be moderate. If it evaporates quickly, then it is difficult to manage this ratio. All right, and we know the rate with which triple alpha process takes place in the star. All right. Now, let us see the level scheme of oxygen 16. Why oxygen 16? Because the C/O ratio 0.6, when we say it is the oxygen which is formed because of the reaction between carbon 12 and oxygen. carbon 12 and alpha particle. Okay, and whether like alpha plus beryllium, is there any resonant state in oxygen 16? Let us see. See, 7162 is the alpha threshold of alpha particle threshold in this reaction of alpha plus carbon 12. Now, 7162, if it is the case, near to 7162 we have two energies 717, 6917. They are bit below the threshold, and above the threshold, if you see, there is no resonance even up to the 2 gigakelvin, even up to 2 gigakelvin, and the centroid of the gamma peak is 1.46 MeV if you consider, if you do the calculation of this temperature, even up to 2 gigakelvin, there is no resonance in the level scheme of oxygen 16. So, what does it mean? Oxygen is not formed. If there is a resonance near the particle threshold, like in the case of carbon 12, Hoyle state which we call, if at all there is a resonance near the particle threshold, then the rate with which this alpha plus carbon 12 proceeds will be very high, but it is not happening. There is no resonance to foster the resonance. So, does it mean oxygen is not formed? No, oxygen is forming. How can we say that? Because it is the most third abundant element in the universe. So, when there is no resonance, because of which oxygen 16 cannot be formed through resonance for higher rate of the reaction. At the same time, oxygen is the third most abundant element in the universe. What is the other way? What kind of mechanism is happening inside this alpha plus carbon 12? It could be some other mechanism, one has to look into it. What are those? We will discuss. Okay. Now, if you see this oxygen 16 at center of mass energy 2.42 MeV and with a width of 400 keV, you see in this level diagram. Okay. There is one resonance, that too at center of mass energy 2.42 MeV, that you keep it in mind. Okay. Now, just below the threshold, like 45 keV and 245 keV, you have 7117 and 6917 keV. So, there are two levels just below the threshold, and we can say that there are sub threshold resonances. We call them as sub threshold resonances. All right. So, as I said, there is no formation of oxygen. No, let us look into the other mechanisms. One is non-resonant direct capture. For example, at center of mass energy 2.4 MeV, okay, you have the state at 9.58 MeV in the oxygen 16. Sigma is in nanobarns. It is very difficult to measure, but once oxygen is excited to this state, during de-excitation through sub-threshold resonances, transition can happen. So, second possibility is non-resonant type of capture into the tail of nearby resonances. When I say nearby resonances, what does it mean? 7.12 and 6.92 MeV, just below the alpha particle threshold. The problem is the cross section of this is expected to be around 10 to the power of minus 17 bonds, which is just impossible to measure. All right. Now, there are challenges in the measurement of this alpha plus carbon giving rise to oxygen 16. What are those challenges? When you take any target, in general, it also contains carbon 13. It also contains carbon 13. And when alpha particle reacts with carbon 13 also, because in the target material when carbon 12 is there and also when carbon 13 is there, it is giving rise to the production of neutrons, and this neutron will induce some gamma background which is higher than this background. Okay. Neutron induced background is one of the big problems in executing this measurement of alpha plus carbon 12. So, one way to circumvent this problem is you swap the target and projectile. That means, instead of using alpha in the particle accelerator as the projectile, take a gas of alpha, helium, and then use carbon 12 as projectile. This is one way. Another way is use high purity carbon 12. Use high purity carbon 12. Highly enriched carbon 12. So, using these two ways one can perform these experiments. Okay. Now, let us see whether quiescent helium burning continues without any problem. No, there is some issue, there is some problems, because of which we observe blocking of quiescent helium burning. Now, here you see alpha plus oxygen 16 gives rise to neon 20, See, ideally we expect in the helium burning alpha plus alpha giving rise to, and alpha plus beryllium, as we discussed, it gives rise to carbon 12, isn't it? And alpha plus carbon 12 is giving rise to 16 oxygen, and alpha plus 16 oxygen gives rise to neon 20. So, like this we expect, right, but things are not so easy. So, after this alpha plus carbon we expect oxygen 16, neon 20, Mg 24, like that, silicon 28, but the reaction does not proceed like this because of the some problem that we are going to discuss in this slide. Okay. So, if you see the reaction of alpha plus oxygen 16, the compound nucleus formed is neon 20, and during de-excitation it can always emit gamma, and the Q value for this reaction is quite low, it is 4.73, it is 4.73. Now, at 4.97, fortunately in the neon 20, at 4.97 there is a state. So, naturally we expect some kind of reaction, resonance reaction, so that we can get high rate because of this resonant reaction. But unfortunately, due to unnatural parity of 2 minus, the reaction does not proceed through this channel. So, this 4.97 channel is gone, and remaining levels, if we consider for the resonances, they are too weak and too narrow at high energies. This is another problem. Okay. So, the remaining possibility is direct capture of oxygen 16, direct capture of alpha by oxygen 16 with cross section. If you see, it is less than nanobonds. So, again difficult to measure the things, right. So, there is no experimental data as of now, and stellar network calculations, they depend on the inputs from the theoretical data. So, I am not going into the details of these reactions because I am trying to give some framework to understand how the blocking of quiescent helium burning is happening. However, as temperature goes up, at high temperature the oxygen plus alpha reaction plays very important role. Alright. For example, when you go to 0.3 gigakelvin, the rate of reaction exceeds even the alpha plus carbon 12. Alright. Only at very high temperature in very massive stars this kind of reaction can happen. So, because of the properties of the resonances, properties of the energy levels in neon 20, the blocking of quiescent helium burning is happening. This one has to understand and remember. Then continue the discussion, what are the other possible reactions which are happening in the helium burning? See, in CNO cycle, if you recollect, one of the major residue is nitrogen 14, and in the helium burning phase, other than helium, 1 to 2% of nitrogen 14 is always there, 1 to 2% of nitrogen 14. So, it also plays some role in the synthesis of elements, isn't it? For example, you have the helium burning, right, and in this helium burning with nitrogen 14, you have F18 giving rise to some gamma ray also. Now, people expected that it can trigger some kind of helium flashes if at all it is below the critical energy required for the triple alpha process, but as of now there is no evidence. Okay. However, this reaction of alpha plus nitrogen 14 is very important for the synthesis of a positron emitter oxygen 18, synthesis of oxygen 18 through the positron decay of F18. F18 is a positron emitter, alright. And here this oxygen 18, synthesis of oxygen 18 is the reason we are discussing this oxygen nitrogen plus alpha, because the purpose of nuclear astrophysics is also to understand synthesis of various nucleides, and here I am discussing the synthesis of oxygen 18. Okay. And the fate of this oxygen 18 depends on this reaction, that is alpha plus oxygen 18 giving rise to 22 neon, because alpha particles are always available. When alpha is reacting with oxygen 18, it is giving rise to neon 22 whose Q value is 9.67 MeV. In addition to that, alpha can also emit neutron by reacting with oxygen 18. So, this is one of the sources for the neutrons. Okay. Now, at low temperature, if you see, capture reaction is dominating, see the negative Q value and the positive Q value, and at high temperature neutron producing reaction is dominating. So, at what temperature ranges oxygen 18, how what kind of reaction it is undergoing, we can see here. Okay? And one of the important sources of neutrons in these stars, which plays role in the synthesis of elements beyond iron, it is alpha plus carbon 13. Where from this alpha carbon 13 has come? All right. So, this carbon 13, when carbon 12 reacts with some kind of lighter particles, all right, we can get this carbon 13, and when it reacts with the alpha particle, whose Q value is 2.21, it is a source of neutrons in the S process. All right. And coming back to the N14, abundant N14 may pose problems because of the high neutron absorption cross section. So, this is an important thing we have to understand. N14, nitrogen 14, which occupies 1 to 2% of the helium burning core, it can pose serious problem because of its high absorption of neutrons, high absorption capability of the neutrons. Okay? And this N14, when it absorbs the neutron, carbon 14 is emitted and it emits a proton, and whose Q value is very less, and this C14, carbon 14, it undergoes beta decay to produce again nitrogen 14, and this nitrogen 14 again can absorb neutrons. All right? And here you can see the production source of carbon 13. So, earlier I said it is the absorption of carbon 12 by, absorption of proton by carbon 12, please ignore it. So, here when proton and carbon 12 reacts with each other in the carbon, when carbon 12 is formed because of the triple alpha process, then nitrogen 13 is formed, and when nitrogen 13 undergoes positron decay, carbon 13 is formed, and when this carbon 13 reacts with this alpha, we get this oxygen 16 producing neutrons. Why this reaction is important? Because these are the neutrons which are playing role in the synthesis of elements beyond iron. So, that is the reason I have discussed this reaction in this slide. Okay? And also carbon 13, when it reacts with proton, as I have shown, okay, here only I am showing. So, as carbon 13 reacts with proton, it gives nitrogen 14. So, the question is, this nitrogen 14 is helping in the production of neutrons or in the absorption of neutrons. So, before postulating any reaction to be major source of neutrons, you have to remember whether that is leading to huge absorption of neutrons also or not. That one has to keep it in mind. All right. Okay. So, after nitrogen 14, what are the other helium burning reactions? As I said, one has to see whether it is a neutron producer or neutron consumer, and neon 22, once it is formed, still helium burning is going on. After reacting with alpha, we can get neutron and also Mg 25, and this is most attractive S process neutron source among theorists. Okay? And where from this neon 22 is forming? When nitrogen 14 is formed, when it reacts with alpha, I have told you fluorine 18 is formed, and during positron decay, it is emitting oxygen 18, and this oxygen 18, if it can capture alpha particle, then it emits neon 22. Okay? So, this is how different processes are happening after the carbon 12 formation, and while surviving the carbon 12, so many reactions are possible within the helium core. All right. Now, let me put some perspectives on helium burning reactions. So, this is a beautiful diagram where it is shown that alpha plus alpha gives rise to beryllium 8. See, it is the small mass difference between 2 alpha particles and beryllium 8. If this is not the case, what is small mass difference? Simple 922 keV. This is one of the major reasons why carbon 12 is created. If the energy difference is more, what is the problem? There is a big problem, because the Hoyle state resonance probability will be less. So, the small mass difference between 2 alpha particles and beryllium 8 and the occurrence of Hoyle state in the carbon 12, these two are main features of this synthesis of elements carbon 12 and oxygen 16. Even if we see deviation from these two, any of these two, it is very difficult to continue the synthesis of elements. Not only that, so you can imagine how our life and universe will look like if mass of beryllium 8 is not very close to the mass of 2 alpha particles, and then enhancing resonant state in the carbon 12, because of this carbon 12 is formed. Now, this parity and isospin conservation laws followed by energy levels in the neon after this oxygen 16, because of which blocking of quiescent helium burning is taking place. So, these three reasons, the very close difference between the beryllium 8 mass and 2 alpha particles, and the happening of resonant state, and the properties of the energy levels which are playing important role in blocking the helium burning, these are important perspectives of the helium burning reactions. So, with this, let me end the topic of survival of carbon 12. Thank you very much.